No. All right, other than a 1. So 1 is kind of always going to be a common factor, and that's why we're actually skipping those first few here for a minute and jumping to this one. However, if we look at our letters, so there is no common factor between a 2 and a 3. If we look at our letters here, a b cubed and a b squared, long term, we're not going to do it this way, but again, this is how you would have learned how to do GCFs back in the day, whenever you would have been taught this in middle school. You would have talked about how I can break b cubed down into b times b times b, and I can break a b squared down into a b times a b. Those are your factors. Then we want which ones are common, and we want as many of them as we could. That's sort of what the greatest common factor means. So notice how we have one set of b's that are common. Then we have two sets of b's that are common. So our GCF in this problem, we would say, is a b squared. We obviously don't want to write them all out every time. So what we're really looking at when we do these moving forward, if I have 3 b's here and I have 2 b's here, do we all agree they each have at least 2? So that's our GCF. So that's what we're going to factor out now. You're going to pull out a set of b squareds. So if I do that from the first one, the 2 would still be there. All right, we haven't done anything with our numbers. And if I had 3 b's and I pull 2 of them out, there would be 1 b remaining. So that's our first term that's left. Then we subtract. The 3 we didn't do anything with, so he would still be there. It had 2 b's initially, but I pulled both of those b's out, so there are no b's remaining for that one. That's it. All we're doing is pulling out that greatest common factor. There's really nothing else we can do on the inside. This is our factored form using our greatest common factor. Okay? And then that's it. If you go to number 6, same thought process. Let's now not write all of these out, but we want to go by each type of expression here. So if I have a 5 and a 15, is there a number that goes into 5 and 15? Okay. All right. So we do have a common factor of 5. So we definitely want to write that down. We also want to consider our variables. So if I look at 6 v's here and 5 v's there, how many do they have in common between both of them? Again, it's a common factor, right? What is it, Jake? 5. Good. So they each have 5 v's. So this is your greatest common factor. That is what we're going to put out in front and then multiply by whatever would be remaining within the parentheses. So if we consider this first term, notice how we started with a 5, but didn't we pull the 5 out? So there's nothing there. You could put a 1. We started with 6 v's. I pulled 5 of them out. So do we agree there would only be 1 v left over? Started with 6, pull 5 out. That means 1 is left. Then I'm going to do minus. If I started with a 15, what would I still have right here if I pulled 5 out? What would this number have to be, Caden? Good. That would have to be a 3. And then if I started with 5 v's and I factor out 5 v's, do we agree there are no v's left over for that term? So we close that parentheses. That is our answer. Okay, that's us pulling out the greatest common factor, and what we have left over, there's not much else we can do with. Okay. All right, so number 7. Greatest common factor. There really is no number, right? There's a 1 and a 1 for both places. So you're only worried about your variables. So we have 4 r's here. We have 2 r's there. So in terms of the number of r's that we have in common, Julia, they each have how many? 2. So r squared is our greatest common factor. That's what we're pulling out. So multiply that r squared out in front. And then of the 4 that we started with, only 2 would remain for the first term. Plus, so now here, be a little bit careful. How many r squareds are left over here for this last term? None, right? However, we can't put an a0, so don't put an a0. Understand how this is important. If I redistribute up here, so if I do b squared times 2b, notice how that would give me 2b cubed. That's the first term. If I then do b squared times a negative 3, notice how that gives me the second term. So if I put a 0 right here, when I distribute, do we agree r squared and r squared gives us r to the fourth, like it's supposed to? Would r squared times 0 give you r squared? No. What has to go here to make sure that if I do an r squared times something that I end up with an r squared, Assad? Yeah, so you would put a 1 right there. We have to hold that spot with a 1. Now if I distribute, I end up with what I started at the beginning. Okay? So r squared plus 1 is what's inside the parentheses. The r squared is our greatest common factor. All right. All right, jump down to number 9. We'll come back to the ones we're skipping, but right now we're going to do number 9. Now we have a trinomial. Just means 3 terms. Same thought process, though. You just have to understand it needs to be common. So that's what the C stands for in all 3 terms. So all 3 numbers, so 21, 7, and 49 would have to have a common factor for us to pull anything out. All right, so is there a number that goes into all 3 of those? Joe, what is it?
7.
Good. So 7 is our number. 7 will divide evenly into all of them. We also have to consider our variables. I have 9 x's here, 5 x's there, 3 x's right there. So in terms of how many are common, we certainly have some that are common. All 3 of those terms have at least how many x's? Was it? I would agree. They all have at least 1, but we can go higher than 1, right, Joe? Yeah, don't they all have at least 3? This one has 3, this one has 5, this one has 9. So x to the third is the greatest number that are common to both, are all 3 parts. Okay? That's our GCF. That is then what you're going to pull out, 7x cubed. And then now we have to think, what's left over? So what would we now have for the remaining terms left on the inside? So first, Nora, 7 times what would have given us 21? 3. So this must be a 3. And if I started with 9 x's and I pull 3 of them out, how many do we have left over, Nora? Good. So that should be a 3x to the 6th. Then I'm going to do plus. All right, and then Maddie, 7 times what would have given us the 7? Good. So there's a 1 left over here. And if I had 5 x's for this term, I pull 3 of those out. How many remain, Nora? Or Maddie? Good. So that's an x squared. And then last but not least, Omar, 7 times what would have given us the 49? 7. And if I had 3 x's and I pull 3 of them out, how many are left over? Good. So we just have a 7 left over for that spot. All right. You following that? All right. Do number 10 then. Yes, sir. All right, number 10. Monica. What do you think, Monica? For the 10, the 5, and the 10, what's the biggest number that goes into all 3 of those? Good. So numerically, we want a 5. All right, then we go to all of our x's. And Jake, if I have 7 x's, 6 x's, and 5 x's, they all have at least how many?
5.
Good. So 5x to the 5th should be our greatest common factor. Okay, so that's what we would have pulled out. So if you did that, hopefully you're on the right track and we get this right. If we then go to this next term here, Ella, what would be left over if I started with the 10, I pulled the 5 out? 2. And then how many x's would we have left over? What is it? Good. We would have x squared. We started with 7, pull 5 out, there's 2 remaining. Minus, and then Jake, 5 times what would given us this 5?
1.
A 1. And how many x's remain?
1.
Good. We had 6, I pulled 5 out, so 1 remained. And then Joe, if I had a 10, I pull 5 out. What number do we have left? 2. And how many x's remain? Good. So there are no x's left over. So that's our final answer. Okay. All right. So hopefully we are understanding that. The ones that I have been deliberately skipping, notice how all the ones we skipped have a negative in front of that. That kind of opens up a little different can of worms. It's a little trickier, not much, but it is something that we want to kind of be careful of. So go to the top of the page and add this problem for me. So let's say I ask you to factor, and I give you, let's do 3x plus 5. And I tell you to find a greatest common factor there. Do the same thing we've been doing. Is there a number that goes into 3 and 5 evenly? No. Do they each have at least 1x? No. So in terms of a greatest common factor, you would kind of say there isn't one. However, there are 2 common factors that exist for every single problem. All right. Can we actually divide each of these by a 1 and it would go in evenly? So one of our greatest common factors can always be a 1. So one option here, instead of writing prime, we could say I'm going to pull out a 1. But if I pull out a 1, that wouldn't change anything on the inside, right? If I redistribute my 1, wouldn't 1 times 3x give me the 3x? Wouldn't a 1 times a 5 still give me that plus 5? So couldn't I technically pull out a 1 if I wanted to? All right. There's also another common factor that would always work. So for this one, I'll do it over here. Same exact problem. If I ask you what is your greatest common factor here, technically you have a 1, but we could also say a negative 1. So now let's pull out a negative 1 from this one, and this is the big one to understand. If I again go back to the original one here, if I did 1 times 3x, do we agree that should give me this first term? Now think about what would happen for this one. A negative 1 times what would make sure that we still get this 3x? What would we have left over in this parentheses to make sure we still get a 3x? Maddie? Good. Couldn't we write that as a negative 3x? So if I pull a negative 1 out, that would change that negative or that 3 to a negative 3. Same with our 5. If I want this to ultimately give me a positive 5, what would need to go right here so that if I did a negative 1 multiplied by that, it'll end up giving me a positive 5. All right, good. That would have to be a negative 5. Okay? So 1 and negative 1 are always common factor. It is rare we'll pull out a 1. It's fairly common we can pull out a negative 1. And that is because, go to number 1 now. Typically for what we're going to do next, we really, really, really want this first term to be positive. And if it's not positive, then we want to make sure that it is positive. Okay? So if you go to this first one, if I ask you for a greatest common factor, numerically, do we all agree that 4 goes into those 2 numbers? Yeah, so let's say we write down 4 to start with. Then there are no letters that are common, so 4 is our GCF. If I pull out a 4, wouldn't I be left with a negative 3b and a negative 4? All right, that's what we go ahead and distribute again, and that's what's going to give us that answer. However, again, what we're going to do very, very soon, we don't really want this guy to be negative. If it is, it's going to cause you much, much more difficulty than we really want it to. So at the same time, couldn't we also say a negative 4 is our common factor? So underneath that, let's say we would have pulled out a negative 4. If that first term ultimately needed to be a negative 12 and I pulled out a negative 4, wouldn't a positive 3b be what would be left over there? Because doesn't a negative 4 and a positive 3 give me this negative 12? And doesn't this 3 now have a positive number instead of it being a negative number? Same here. If I want this to be a negative 16 and I pull out a negative 4, wouldn't that change this to be a positive 4? You can check these real quick again. The negative 4 times 3 will give me a negative 12 like it's supposed to. The negative 4 times a positive 4 will give me the negative 16 like it is supposed to. These are both equally correct. So this is not wrong, it's correct. This is also correct. Long term, though, actually not even long term, by the end of the week, we really want this to be a positive number. So we would want to pull out that negative factor. Okay. So when you go to number 2, as soon as we see that the leading number here is negative, then when we go to identify our greatest common factor, we would hopefully know that it's a 4n for sure. 4 goes into itself, and then they each have 1 n. But since this leading number is negative, we really probably want to take out a negative 4 versus the positive 4. So if I now pull out the negative 4n as my common factor, think about what would need to be left over. So what you're thinking here, negative 4n times what would give me a negative 4n squared. Write that down. See if we're understanding what that would have to be. All right, what do we think? A negative 4 multiplied by what would give us a negative 4? Armando? Okay, good. I'm going to put a 1. He just put n, which is 100% correct. But just so we can kind of understand, negative 4 times 1, wouldn't that give us the negative 4? And then we had 2 n's, and I pulled one of them out, so I'd only have an n left over. So the 1 isn't critical. That's why Armando just said an n. I like putting the 1 so that we know that those two give us the negative 4, though. All right, next thing. Write down what would have to be remaining so that if I did a negative 4n, I end up getting a positive 4n. So what would I multiply negative 4n by to get a positive 4n? All right, you got that one, Armando?
Yeah, negative 1.
Good. That would have to be a negative 1. And then just test it. Doesn't a negative 4 times a negative 1 give you a positive 4? And then the n going here gives us the 1 n that we needed. All right. Okay, so take a minute, try number 3. Without us getting you started, see if you could do number 3. Then you can check real quick, can you distribute your answer? And when you take your answer and distribute, will it give you the original problem? And if it does, there's a reasonable chance it's correct. Okay, as long as you pull out the biggest factors. Okay, can anybody do that legitimately? And then give me what that GCF would have been then, if you did that correctly. Anybody? Armando?
Negative 4x.
Good. So between 4 and 16, that's a 4. But since that leading term is negative, it means we probably want to pull out a negative 4. And then we each have at least one x. So we tack on one x for our greatest common factor. So that's what we're going to put out in front. If I want my 4 in the answer to be a negative 4, then I would have to do a negative 4 times a positive 1. Oops, I forgot to put the x. Hold on a minute. So negative 4 times 1 gives me the negative 4. And then Armando, how many x's would remain?
X squared.
Good. Because I started with 3. I pulled one of them out. All right. Then a negative 4. What remains here, Armando?
Positive 4.
Good. Positive 4. So that a negative 4 times a positive 4 gives me a negative 16. I started with 1x, I pulled that out, so there are no x's remaining. All right. Okay, last one before we kind of move on. You're going to get some more practice of this. Go down to number 11, see if you could do 11. So again, what we're identifying, that leading term is negative. So whatever you think your GCF is, we want to make it a negative of that number. All right, Kira, what'd you write for your GCF? Good. So 3 is the number that goes into all three of those, the largest one. Since the leading coefficient is a negative value, that's why we want to pick a negative 3. And then notice this had 2 n's, this had 1 n. Does this one have an n at all? No, so they don't have a common n at all, so good. The only common factor is a 3, or in this case, a negative 3. So that's what we're going to pull out. All right, then a negative 3 times what would have given us a negative 6, Kara?
2.
Good. And then the n squared wouldn't have changed. And again, you can check real quick. Negative 3 times 2 does give us a negative 6. All right, negative 3 times what would give us a positive 9, Kara? Good. So negative 3, and then the n would still be there. And the last one, Kira, negative 3 times what would give us that negative 9?
3.
Good. Positive 3, and then that's your answer. All right. Okay. Got a handle on that a little bit. Okay, then. Yeah, sure. Thank you. All right, this is where things get a little more wild and challenging. They're all mixed together. So if you look, there's a little bit of everything now we've done. We've done trinomials, we've done differences of squares, and we've done a GCF. All right, and what I've kind of done is just thrown them all together. And we need to be able to diagnose what we're looking at and then how we can handle that. So to guide us with that, so basically this whole assignment, here's your thought process at the top of the page. First thing says, when factoring an expression, the first thing you are always going to look for is a greatest common factor, what we just did. So every single problem, so I got like 30 problems here. The first thing you are looking for is, does this thing have a greatest common factor? All right. Then all of these are either trinomials. Trinomial means there are 3 terms, right? Tri means 3 terms. Or they are binomials, bi meaning 2 terms. So if we look at number 1, that's going to be 3 terms, so that's a trinomial. Here's your thought process. You are again looking for a GCF first. That's again the first thing you're looking at for every single one of these problems. If there is one, you're going to do it just like we did. Then once you've done that, we want to identify, I'm going to just kind of call it the little product sum idea that we need to multiply, maybe draw a little box in here to kind of indicate the way we think this through. It multiplies to be the bottom right-hand corner. Make this nice and big. And then it has to add up. It has to have a sum of these 2 boxes here to be the middle term. That's how we would approach trinomials. If it is a binomial, the first thing you're going to look for, does it have a GCF? And then the second thing is what you turned in for homework today. Identify, is it a difference of squares? And and we have a method for that as well. So difference of squares, write this out just kind of as an example. So this is what you should have done a bunch last night. If it's a difference of two perfect squares, then we would do a minus b and then a plus a b. So that's how our differences of squares work. All right. So every problem of these, if you ever get stuck, this is your thought process. Am I looking at a trinomial or am I looking at a binomial? We go through these steps. All right, so if you look at number one, I see right away the very first problem, I have a little typo there. There should be an x in this middle term, so this should be a 13x. All right. So it's a trinomial. There is 1, 2, 3 terms. So our thought process is, if I'm looking at a trinomial, look to see if there is a greatest common factor. All right, so when we look at that, is there a greatest common factor in all three of those terms? No, there's not a number. They don't all have an x, so there is no way to factor that with a GCF. So then we go to the little product sum idea. So a little review, and it's again up to you. Looking at the homework, that's what I gave you back yesterday. A lot of us don't do the box anymore. We got pretty good at it where we don't need to. But that's where this originated from, that the x squared is x and x. That's always the first term multiplied together. The x and the x would give us that corner. The bottom right-hand corner is a negative 30. And that then is what numbers would I multiply up here and here to give me a negative 30, but at the same time, multiply together to give you a 13. All right, we did pretty well on this assignment. So come up with that combination real quick, because these we were pretty good at. You have that factored little chart too. That's what that was factored. That's what those are for, that factor chart. All right. Anybody think they got that? They need to multiply to be a negative 30, but they need to add up to be 13. And it's not prime. No, don't like that one. Assad?
I was going to ask, where's the sheet for this?
Were you not here when I gave it out?
No, I wasn't going to
All right, Armando?
X plus 15, x minus 2.
Good. Positive 15, negative 2. Multiply those together. They give us this box, negative 30. And then this would have been a 15x and a negative 2x. When I add those together, it gives me a positive 13x. So then he said x plus 15, x minus a 2. Box, totally fine. It's a nice way to organize it. But again, if you can go right to this, feel free. Okay. We go to number 2. It is a binomial. So if we look at the little guide we have at the top of our paper, for a binomial, we first look to see, is there a greatest common factor? All right, is there a greatest common factor between a squared and 49? No. So then the only other option is, do we have a difference of squares? So that would mean that we need a difference, which we definitely have. And then this is a perfect square, and then that is a perfect square. So this one factors pretty quickly to be an a minus 7 and an a plus 7. All right, so the first one is a trinomial, second one is a binomial. Those are our two methods if a GCF isn't there. All right, 4. Try number 4. I'd be very impressed if we got this one. So see what you think for 4. Then, well, I'll give you 30 seconds here. Someone's still writing. I'd like to see if we come up with this one before I give the answer. All right, this is your answer. If you got this, I'm impressed. Okay, especially this first day of kind of throwing all these rules together at once. All right, this would be your final answer. If you got it, really, really good. And if not, I promise you're not alone. Okay. But again, as long as we follow our steps up here, okay, how many terms we got? We got one term, we have two terms. So that is a binomial. Here's the only two methods we know for binomials. First, identify if there is a GCF. So just follow these steps. Is there a GCF here? Yeah. Aren't each of these divisible by 2? So I'm going to be able to pull a 2 out. And then they each have how many b's in them? Omar? They have at least one. We can go higher than one though, right? Yeah, 3 said. Yeah, so they each have 3 b's. So I can pull out a 2b cubed. Well, if I pull that out, the only thing left over for that first term, haven't we basically pulled everything out from the first term? So the only thing we would be able to have left over is a 1. And then I would do minus 2 times 4 would give me the 8. And if I started with 5 b's and I pull 3 of them out, I would have 2 b's remaining. That's our greatest common factor pulled out. Don't change yours, but just so you, again, if I distribute, doesn't this give me 2b cubed? And then the 2b cubed times the 4b squared will give me the 8b to the 5th. All right, so we pulled it out, no issues there. Then we now have to look at, now that we've taken the difference of squares, now we ask ourselves, is there a difference of, we pulled out the GCF, now we ask ourselves, do we have a difference of squares? So if we look at this problem, don't we have a difference? Then isn't 1 a perfect square? Isn't 4 a perfect square? And isn't b squared a perfect square? So we do have a difference of squares once we pull out that GCF. So the 2b cubed gets dropped down. And then this is your homework from last night. What I square to get a 1 is 1. So those are the first term of each. What we square to get a 4 is a 2. And what we square to get a b squared is a b. And then every problem you did last night, 1 is a sum, 1 is a difference. Okay, so then this ends up being our final answer. All right. Not easy. Okay, follow that, hopefully. Okay, 5 should be easier. Try number 5. So trinomial, look at what our list says at the top of the paper. How do we handle trinomials? And we're just going to go through those steps. Oh, did I skip 3? Shoot. Okay. This one, hopefully a nicer one. First, look for a different greatest common factor. Was there a greatest common factor in all 3 of those terms? No. All right. There's no x's in all of them. There's no number in that first term other than a 1. So other than 1 and -1, there is no common factor. It's then a trinomial. So if we go to our list, once we identify there is no common factor, now we're just doing this little method right here. So we're looking for 2 numbers that multiply to be a -20, but would add up to be a -8. and those do exist. So the first two terms here multiply to give us the x squared. So what numbers would multiply here and here to give us a negative 20, but when I add them up, they're going to give me a negative 8? Armando?
X minus 10, X plus 2.
Good. X minus 10, X plus 2, they multiply to give you a negative 20. If we add those, they're going to give you the negative 8. Okay? All right, 6. See what you think in 6. It's a binomial. Look at your list for binomials at the top of the paper. Do each of those, and if we do them correctly, we should end up with the right answer. All right, let's see what we got here. It's a binomial. That means the first thing we look for is a GCF. So, Jada. What do you think, Jada? Is there a number or letter that's common to both of these guys? Okay, good. So -1 absolutely would work. 1 is going to work. The 1 we will hardly ever pull out. The -1, the only time we would want to pull it out. So you're not wrong necessarily. The only time we want to pull out the negative is if this first number was negative. So if that was a negative 36, then yeah, we'd want to pull that out. Okay. So other than 1 and -1, was there any other number?
Well, what would you do if because the y is only 1, so what would you
Good. There isn't one. That's why you're having a hard time coming up with that. Yeah. So that's why only 1 and -1 are really our options. And again, we never really want to pull out a 1. There's no reason to ever do that. And the only reason we would ever pull out a -1 is if the 36 was negative. Right. So it's basically you saying there isn't one. All right. She couldn't come up with it. So once we know there isn't a greatest common factor, then we identify, is there a difference? There is a difference. And it is a difference of perfect squares. So is 36x squared and y squared, are those both perfect squares? Yeah, right? So this is what we did for homework last night. We then go ahead. We know that one's going to be a sum, one's going to be a difference, one's a plus, one's a minus. And then what do we square to get 36? And that's what, Jada? Good, Jada. And then we square an x to get x squared. So the first two terms are 6x's. And then the way we get a y squared is with y times a y. So we factor this as if it is a difference of squares. Okay? And then that's it. Those are our two options. We're done. All right, you would move along then. All right, 7. Same thing. Try number 7. It's a binomial. Same two steps. Is there a GCF? Is there a difference of squares? Let's see where we're at. Omar was, so again, here's our steps for a difference for a binomial. So we have two terms here. We first look for a GCF. Was there one, Omar? What is it? Good. 2 goes into both of those numbers. There is no k common to both though. So we're just going to pull out a 2. If I pull out a 2, what's left over, Omar? What is it? Good. K squared for the first term minus 121 for the second term. All right. So we're now done with this method. We've done this. It worked. So now we go down to our second option. That doesn't necessarily mean we are done. We now want to identify, do I have a difference? Do we have a difference? Yeah, there's a minus sign right here. And are the two terms nice, perfect squares? So are k squared and 121 nice, perfect squares? Yes. So this can actually go further. So the initial 2 goes out in front. And then how would that factor, Omar? Good. K plus 11 times k minus 11. That is then our final answer. Okay. Okay. Bring this tomorrow. I want to, these are easy when they're taken by themselves. When they all get thrown together, this is one of the harder things we do. Okay. So bring this tomorrow. We'll hammer out some more of these and hopefully we get to be better at this. Okay. Skip number 3 for some reason.